Hello everyone, welcome to the lecture 2 of the matrix video. In my previous video, I told you that I will be discussing the Cayley-Hamilton theorem in my next video. So in this video, I will be discussing the Cayley-Hamilton theorem and the related problems that appear in the CSIR NET exam. And there is a special problem where I will be discussing a special technique that will be helpful to solve those types of problems. So let us begin. So first I would like to discuss what is the Cayley-Hamilton theorem, what the theorem states. It states that every square matrix that is of the similar dimension n cross n satisfies its own characteristic equation or eigenvalue equation, right? So what is the eigenvalue equation? This is the eigenvalue equation, that is the matrix determinant of the matrix minus lambda into identity. This equation I have already discussed in my previous videos, right? So what is the use of this Cayley-Hamilton theorem? This theorem is helpful in finding the inverse of a matrix, right? So how it is helpful? I am going to show this with this example. Suppose A is a 2 cross 2 matrix and it has elements 1, 2, 3 and 1. Then writing the characteristic equation of this matrix, that is determinant of A minus lambda into I. As A is 2 cross 2, so identity would be 2 cross 2 matrix. Then I am putting back the elements here, that is the matrix A 1 2 3 1 minus lambda into identity, that would be lambda 0 and 0 lambda. If you solve it, and this would be the final matrix in the determinant, that is 1 minus lambda 2 3 into 1 minus lambda. Then if you solve this, that is this into this minus 6, and if you solve this, this is the final equation, right? Now as you can see, the Cayley-Hamilton states that every square matrix satisfies its own characteristic equation. That is, what is the aim of characteristic equation? The aim is to find the eigenvalues of the corresponding matrix. That is, if according to the Cayley-Hamilton theorem, the matrix satisfies its own characteristic equation, that means the matrix is equal to the eigenvalue of the equation, right? That means the matrix is the zero of the characteristic equation, right? So if you put lambda is equal to A, then it would be A square, right? In place of lambda it would be A, so A square minus twice A minus 5i is equal to 0. Then if you multiply with A inverse from the left, then A inverse into A square would be A minus 2 into A inverse. A inverse would be identity matrix minus 5 into A inverse into A, it would be A inverse is equal to 0. Now if you sort the A inverse out and separate it out, you would find the value of A inverse as A minus twice I by 5. So you can see that with the help of Cayley-Hamilton theorem, you can easily find the inverse of a matrix. So this is the main motivation of using Cayley-Hamilton theorem, that you can find the inverse of a matrix very easily, right? So let us move slowly to the problem section of the Cayley-Hamilton theorem. This video is a short video. This is the extension of the first video of the matrix. And here I will be discussing some problems related to the Cayley-Hamilton theorem. So welcome to the first question on Cayley-Hamilton theorem, and it is one of the most easiest questions that you can get. It came in CSIR NET December 2016. So the question is, the matrix M, it is a 3 cross 3 matrix, satisfies the equation. So you may see you have some matrix equations and it is given in terms of M. Generally the matrix equation comes from the eigenvalue equation, where the equation is in terms of lambda. But as you can see, the matrix equation is in terms of M. That means M, the lambda is replaced by M. And instantly you have to guess that this is Cayley-Hamilton theorem, because in Cayley-Hamilton theorem we replace the eigenvalue lambda with the matrix M, right? Or the matrix, whatever matrix it is given. So if you use the characteristic equation, M minus lambda is equal to 0, and if you put the matrix minus lambda into identity, identity is also 3 cross 3 because the matrix is 3 cross 3, then you get the following equation, that is minus 1 minus lambda into 1 minus lambda square minus 9 into 1 minus lambda is equal to 0. And if you solve it out, you get this equation, right? But you can use the Cayley-Hamilton theorem because in the option the answer is in M, and if you replace lambda by M using the Cayley-Hamilton theorem, then you will get M cube minus M square minus 10M plus 10 into I. There is nothing there, so I am replacing 10 into I. So these two equations are similar, just replaced lambda by m. So C option is the correct option. So this is one of the most easiest questions that came in CSIR net, right? It came in CSIR December 2016 and it is on Cayley-Hamilton theorem, right? For me, this question is the motivation for making this video, right? Because I've used here the Cayley-Hamilton theorem to solve one of the most difficult questions if you solve by general technique, that is by expansion method or by diagonalization techniques. So it came in CSIR June 2011 that consider the matrix M. It is the matrix M contains all the elements as 1. The exponential M simplifies to, right? The exponential M. That means you have to find the function exponential M. So you have to use the form 2 of the Cayley-Hamilton theorem. That is, the function is the summation of alpha, and alpha n is a coefficient, multiplied by m to the power n. That is, m is the matrix m to the power n. Then if you expand it, the function here is e to the power m, right? But you may be asked to find any of the function, that is sin m, cos m, tan m, log m, right? Sine hyperbolic m, it can be anything. That is why I've written a function. The function can be anything. Then e to the power m is equal to alpha naught plus alpha 1 m, right? If you put the n is equal to 0 and 1 here. Then the next step is to find the eigenvalue of the matrix, right? If the matrix have all the elements as same, then the eigenvalues are the trace of the matrix and the rest of the eigenvalues are 0. The trace is 3 and the rest of the eigenvalues are 0. So if I put the first eigenvalue, that is m is equal to lambda 1 is equal to 3, in this equation it is e cube is equal to alpha naught plus 3 alpha 1, right? And if I put the second eigenvalues, that is m is equal to lambda 2 is equal to 0 in this equation, because in Cayley-Hamilton theorem we replace m by lambda, right? Then it is alpha naught is equal to 1. Now if I replace alpha naught is equal to 1 in the equation number A, then I get the value of alpha 1, right? And this is my this is the motivation, that I have to find the alpha naught and alpha 1. After finding alpha naught and alpha 1, I put them back in the original equation, because I have to find e to the power m, where these coefficients need to be found. So e to the power m is alpha naught is 1 plus alpha 1 is 1 by 3 cube minus 1 multiplied by n. This is the final form of the function that you are asked to find, right? That you are asked to find, right? So e to the power m is equal to 1 by 3 e cube minus 1 m plus identity. So you can see that using Cayley-Hamilton theorem, I can solve a difficult question in a less amount of time. So this video is a short video, and I hope you have enjoyed this video. If you have any doubt, you can post it in the comment section. And if you like this video, you may share this video with your friends. And if you like the content on this channel and want more updates, right, you may subscribe my channel for getting more updates. So thank you. Bye bye.